Hello guys, you're welcome back to my channel Fun with Physics. In this lesson we're going to look at the principle of moment. In my last video I talked about levers and was able to establish certain facts about levers. For instance, we were able to establish the fact that levers are force or effort multipliers. Also, some few levers are distance and speed multipliers. Not only that, we were able to come up with the fact that levers work basically on the principle of moment, that is on the turning effect of force. For instance, you have a crowbar and you want to use it to lift a load. All you need to do is to apply an effort on the longer arm, okay, and that will create a turning effect to move the load upward at the other end, at the shorter arm from the pivot. Okay, now basically moment is what we are going to consider in this lesson, and it is simply the turning effect of force. Okay, now look at these simple machines here, these levers. This is a spanner and this is a wheelbarrow. This is a tire, a wheel of it, a tire and a wheel. Okay, now if you have a spanner and then you apply a downward force this way at this distance from the pivot or the fulcrum, okay, the middle of the knot. Now you observe that there's going to be, when you apply a force, it's going to cause a turning effect. Okay, in that way you'll be able to loosen this knot. A clockwise turning effect. Can you see it? An arrow showing clockwise turning effect. This is because it's moving in a clockwise direction, right? The same thing applies to this. When you take the handle of the wheelbarrow up, it's going to cause a turning effect about this pivot. Okay, the wheel here is a pivot. A turning effect, clockwise turning effect. Okay, the distance from this pivot to the handle of the wheelbarrow is this, from here to here, isn't it? Look at it, the distance, the perpendicular distance from the point where the force is applied. Okay, now let's see some few more examples of where we have a turning effect caused by an applied force at a given distance to the pivot. Now look at it, the door in the picture here. The pivot is the hinge, right, at a distance d from the door. When you try to close the door, that is apply a force here, you observe that there's going to be a turning effect, isn't it? The same thing applies to this seesaw. This is the pivot, and the distance from the force is actually the weight here downward, is this. The distance from the pivot to the force is d, given here. Okay, notice this one also. A spoon is used to open the cover of a can for an object. Now notice that a downward force is applied at a distance d from the pivot. This position is the position of the pivot or fulcrum, as you may call it. Okay, now when you apply a downward force, there is this counterclockwise moment or anti-clockwise moment that is formed, an anti-clockwise turning effect that is created. Can you see it? Notice the direction of the arrow, anti-clockwise turning effect. Okay, now and many more examples like this. Now in this case now, what is moment? Like I said before, moment is simply the turning effect of force, and all levers apply this principle to be able to function. Okay, now moment can also be defined as force times perpendicular distance from pivot. If force is in Newton and the distance is in meter, then we can guess the unit of moment. Can we figure out the unit? Force is in Newton, distance is in meter. Of course, the unit is going to be Newton meter. Okay, other units are Newton centimeter, Newton millimeter, and so on. Now, a sample example. If you have a spanner of length 0.15 meter, and then you apply a force of 50 Newton on one end, it will exert a moment. Okay, so we can actually calculate the moment. The moment will be 50 times 0.15. Okay, that is the force times the perpendicular distance to the pivot. Notice that this is the pivot, the position of the pivot, isn't it? So the moment is 7.5 Newton meter. Okay, now how about if you use a longer spanner? What happens to the moment? Will you have a greater turning effect or a smaller turning effect, lesser turning effect? Okay, let's check it out. A distance of 0.25 meter and the force is 50 Newton. If you substitute this in this formula, you have 1.25. That is moment, force times distance. You have the moment here as 12.5 Newton meter. Okay, which is twice the other one, or more than, up to twice the other one, almost up to that. Okay, it means if there's any case where we can double the distance, the moment will be doubled. Now let's go back to this. Now from this figure here, moment is directly proportional to force, right? At the same time, moment is directly proportional to the distance, perpendicular distance. So in that case, if I double the force I'm applying on one side of the spanner, the moment will be doubled. If I also double the distance, the moment will be doubled. Okay, because they are directly proportional. So here I almost doubled the distance and the moment was almost doubled. Okay, the principle of moment. Now if an object is in a balanced state, that is neither tilting to the left or to the right, the principle of moment states that the total clockwise moment about the pivot is equal to the total anti-clockwise moment about the pivot. Okay, like this guy here carrying a ladder, and on one end of the ladder we have a bucket of water. Okay, now he may or may not be supporting it with the other arm. From the look of things here, he's not supporting it, and the ladder is balanced, not tilting, not moving down, not tilting to the right hand side or to the left hand side. Okay, now the distance from the shoulder, which is the pivot, to the middle of the ladder where the weight acts on is 0.6, and also the distance from the pivot, the shoulder, to the point where the bucket was placed is 0.9. Okay, so we can calculate the moment. We can check it out. Anti-clockwise moment, that's this one, the turn to the left hand side, this turn here, equals to clockwise moment according to the principle. Okay, let's use that and see what will happen. If you substitute 150 by 0.6, you multiply by 0.6, remember moment is force times distance, perpendicular distance, and you do the same thing in the clockwise moment, the clockwise side. Okay, the right hand side, 100 times 0.9, you observe that the values are going to be the same. So 90 Newton meter is the same thing as 90 Newton meter in the other direction. Okay, now this goes to show that if an object is balanced, the clockwise moment, or the sum of the clockwise moments, is always the same thing as the sum of the anti-clockwise moment. Are we good? All right, we can figure this out in by carrying out a a little experiment or practical in the investigation, as you may call it, in the lab to check if it is true. You may have several loads, a weight and a counterweight to see if the principle is true. Now let's revise our last lesson to solve some problem. You may or may not solve this. You may solve it mentally, or if you have your exercise book, you can also solve it there. Now here in this question says calculate the force F. We know that clockwise moment, the turning effect on this side, is the same thing as anti-clockwise moment, the turning effect on this side, if this object is balanced. And from the look of things, this object is balanced. It's balanced because it's neither moved tilted to the left, to the right, or to the left. Okay, standing perfectly horizontal. Okay, so applying the principle of moment, for the clockwise you have F times 8, for the anti-clockwise you have 20 times 12. You can equate it and solve for F. Okay, now for question number 2, find the weight of the monkey. You can also apply the principle of moment here. W times 1.2 for the clockwise moment, 350 times 2 for the anti-clockwise moment. Equate both and solve for W. If you only have a measuring tape, how would you find the weight of the boy? Any idea? Okay, of course we can get the weight of the boy by measuring the distance from the middle of the boy to the pivot here, or knife edge, or support, whatever you call it, and then apply the principle of moment to calculate the weight. From the principle of moment, the clockwise should be 240 times 1.5, and the anti-clockwise should be the distance from the middle of the boy, from this point to the pivot, times whatever the weight is. We don't know the weight, but we can actually measure the distance. Okay, so equate both and solve. All right, now let's look at this question. In this question we have 4 newtons supported at the right hand side of a beam, and then 2 newtons supported at the left hand side at different distances. Okay, so from applying the principle of moment, we can check and see if this support is actually in equilibrium or balanced state. So let's do that. For the right hand side, we know that the right hand side represents the clockwise direction, turning effect, right? It's going to turn this way, right? And the left hand side, if it's turning this way, if it's falling towards the left, it represents the anti-clockwise turning effect or anti-clockwise moment. For the clockwise, we have 4 times 3, which gives us 12. For the counterclockwise or anti-clockwise, we have 2 times 2 plus 2 times 4. Okay, notice that I have to add it up. Remember that the principle states that the sum of the clockwise and the sum of the anti-clockwise. So where we have more than one force, we should look for more than one moment and sum them up. Okay, so here we have to sum up the moment of this 2 Newton force about the pivot and that of this 2 Newton force about the pivot. Okay, at the end of the day we have 12 Newton meters. So comparing our results, 12 Newton meter and 12 Newton meter, it goes to show that the beam is balanced. Okay, now we can try this out on our own. Okay, try it out on your own and see what's going to be your final result. Try to apply the principle of moment. Okay, here we have 2 forces. So for the clockwise we should have 2 times 3 plus 3 times 8. For the counterclockwise or anti-clockwise, we should have F2 times 4 meter. Equate both. If this is in equilibrium, and of course it is in equilibrium, it's in the balanced state, equate both and then get your F2. Okay, can you try it out? Try to see what you can do in your test, in your exercise book. Okay, and finally we can apply the principle of moment to get the perpendicular distance from the point where a force is applied. In this question, this is supposed to be where the distance will end, but we extended it. It's not supposed to. There's a little error somewhere here. Okay, so we can use it to get this distance from this point to this point. So apply the principle of moment and try to use it to find this. Okay, to find this x, the distance from the 200 Newton to the pivot, the perpendicular distance. Are we good? If you have, in case you have any question, please comment in the comment section or in my page in Google Classroom. Please type your comments, your questions. I'll definitely attend to them. Thank you.